as with my sum and difference of angle identities, it was useful for me to at least go through one proof where I verified that our function could be written in a certain way. We want to go through and verify some of these proofs. So let's talk about this first one right here. We have the sine of 2 alpha is equal to 2 sine alpha cosine alpha. Where did that come from? Well, in the last section, we would have said that the sine of u plus v is exactly the same as talking about the sine of u times the cosine of v times the cosine of v added to the cosine of u times the sine of v. So how does that help us? Well, in this case, sine of 2 alpha. What is sine of 2 alpha? Sine of 2 alpha is really the same as saying the sine of alpha added to itself, right? 2 times a number is equal to itself plus itself, right? Just multiplication is fancy addition, maybe you might have heard me say. Well, if that's the case, then by this double angle identity, we actually have, by this sum of angle identity, we actually have the sine of alpha times the cosine of alpha, right? It's the sine of the first angle times the cosine of the second angle, added to the cosine of the first angle times the sine of the second angle. Well, the first and the second angle are both exactly the same. It doesn't really matter which order we add sine of alpha, we multiply sine of alpha and cosine of alpha. It's the same either way. So the sine of alpha times the cosine of alpha is the same as the cosine of alpha times the sine of alpha. So I could just simply replace this second statement, and lo and behold, it's exactly what we have, 2 sine alpha cosine alpha. So the sine of 2 alpha is 2 times the sine of alpha times the cosine of alpha. And just remaining true with my identity, this is sine of 2 alpha. And that's exactly what we set out to verify right here. All right. So for sine, that one's fairly easy. And you can actually see the family resemblance of tangent of u plus v with tangent of 2 alpha. These other two for cosine might be a little bit more challenging. So let's just quickly talk about those ones. What about the sine and about the cosine? Well, if we use this formula right here and replace it with alpha plus alpha, we can still see the same sort of thing that we were talking about. If we take the cosine of alpha plus alpha, which is the cosine of 2 alpha, we're going to get cosine of alpha by this formula times the cosine of alpha minus the sine of alpha times the sine of alpha. And that is the square of the cosine of alpha minus the square of the sine of alpha. Now, you might note, well, this looks an awful lot like that other Pythagorean identity, but except you must remember there, that was where we had cosine squared alpha plus sine squared alpha. So that doesn't change the sign and give us -1. That's not what this says at all. This says if you take the difference of the two squares of the cosine minus the sine, you get cosine of alpha plus alpha, which is cosine 2 alpha. How do we get this first one right here? Let's just work that one out. Well, in that case, we can modify this just a little bit by using a Pythagorean identity, simply because we recognize that we have the square of one of these trigonometric functions, and sine squared alpha is the same thing as 1 minus the square of the cosine of alpha. So we can actually verify that second formula just by using our Pythagorean identity, and then distributing the negative through multiplication. So we'd have -1 plus the square of the cosine of alpha. And since we have 2 cosine squared alphas, we get 2 times the square of the cosine of alpha -1. And again, there's a very similar proof that you can show for the last one. which is an exercise for you guys to do. And then, of course, there's the tangent to alpha. So please carry those out, and we'll have more in the next video.